Let's continue with task statement 1.1, which is to explain basic AI concepts and terminologies. As we've seen, the output of a machine learning model is an inference. In our fish example, we trained our model to recognize images of fish by training it with images of fish swimming in the water. However, our deployed model might see images of fish that are a bit different, like a fish out of water, and not recognize them as fish. When a model performs better on training data than it does on new data, it is called overfitting, and it is said that the model does not recognize well. The model fits the training data too well. So when it sees something slightly different, it thinks the probability is low that it is a fish. Usually, the best way to correct a model that is overfitting is to train it with data that is more diverse. Sometimes, if you train your model for too long, it will start to overemphasize unimportant features called noise, which is another way of overfitting. Underfitting is type of error that occurs when the model cannot determine a meaningful relationship between the input and output data. Underfit models give inaccurate results for both the training dataset and new data. This can happen if you haven't trained the model long enough or with a large enough dataset. Because training for too long can cause overfitting, data scientists try to find the sweet spot for training time where the model doesn't underfit or overfit. Bias is when there are disparities in the performance of a model across different groups. The results are skewed in favor of or against an outcome for a particular class. As an example, consider a machine learning model for automatically improving loan applications. The training data will have examples of loan applications that should be approved and those that should not. If the training data doesn't have enough applications from diverse population, the model could learn a pattern that is biased against a particular group. For example, the loan application contains features like the customer's income, job history, age, gender, and location. Suppose that there aren't any approved applications from 25-year-old women living in Wisconsin in the training data. Then the model could learn that those should not be approved, even though other features such as their income and job history would qualify them. The quality of a model depends on the underlying data quality and quantity. Also, if a model is showing bias, the weight of features that are introducing noise can be directly adjusted by the data scientists. For example, it could completely remove gender consideration by the model. Fairness constraints, such as age and sex discrimination, should be identified at the beginning before creating a model. Training data should be inspected and evaluated for potential bias, and models need to be continually evaluated by checking their results for fairness. I'm going to pause this lesson here, and in the next lesson, we will continue talking about task statement 1.1. Let's continue with task statement 1.1, which is to explain basic AI concepts and terminologies. And let's concentrate on a specific type of machine learning, deep learning. Deep learning is a type of machine learning that uses algorithmic structures called neural networks. These are based upon the structure of the human brain. In our brains, brain cells called neurons form a complex network where they send electrical signals to each other to help us process information. In deep learning models, we use software modules called nodes to simulate the behavior of neurons. Deep neural networks comprise layers of nodes, including an input layer, several hidden layers, and an output layer of nodes. Every node in the neural network autonomously assigns weights to each feature. Information flows through the network in a forward direction from input to output. During training, the difference between the predicted output and the actual output is then calculated. The weights of the neurons are repeatedly adjusted to minimize the error. Deep learning can excel at tasks like image classification and natural language processing, where there is a need to identify the complex relationship between data objects. In our fish example from earlier, we saw that we can train a machine model to recognize objects in an image. But training the model required a lot of human effort to label thousands of images. This is the way that image classification, object detection, and other forms of computer visions have traditionally operated in the past. The concept of deep learning with neural networks has existed for some time. However, the required computing power wasn't feasible for most businesses to obtain until the arrival of low-cost cloud computing. Because anyone can now readily use powerful computing resources in the cloud, neural networks have become the standard algorithmic approach to computer vision. A big advantage of deep learning models for computer vision is that they don't need the relevant features given to them. They can identify patterns in images and extract the important features on their own. However, we might need to give a deep learning model millions of pictures of fish before it can accurately detect and label a fish in an image. And the compute infrastructure to train a deep learning model repeatedly on such a large data set is going to cost more than the traditional approach. The decision to use traditional machine learning or deep learning depends on the type of data you need to process. Traditional machine learning algorithms will generally perform well and be efficient when it comes to identifying patterns from structured data and labeled data. Examples include classification and recommendation systems. For instance, a cell phone company can use ML to predict when a customer will change carriers based on previous customer churn data. On the other hand, deep learning solutions are more suitable for unstructured data like images, videos, and text. Tasks for deep learning include image classification